Good morning to all of you.
Good morning, sir.
Good morning. So are there any questions, doubts anybody want to ask on whatever we have discussed so far?
Sir, I have a doubt in the like number 22A, the viscoelasticity chapter. When we
Yeah, what
write
is
the,
your doubt?
so when we write the Prony series, so
Yeah,
we said that we find the material constant like infinity E1 E2 from the stress
yeah,
relaxation curve.
yeah,
So
yeah.
actually, how should we how can we find out the material constant?
You have to buy curve fitting, no? So you have to minimize the difference between the experimental data points and the one predicted from this Prony series. So you will get sigma xx as a function of t equal to Et, where Et is in terms of Prony series into epsilon xx, constant strain. So in this, you have got the experimental stress versus time graph, and you have got now you have to fit these E infinity, E1, E2, tau 1, tau 2, etc. such a way that the experimental curve is matching with the theoretically predicted curve.
Okay, means from curve fitting.
Yeah.
Okay.
Any other question? Anybody? हेलो सर मेरा क्लास है। हाँ सर, एक 12:15 किसी को बुलाया हुआ है, तो मैं उसके बाद जैसे वो खत्म हो जाता है मैं आ जाऊँ।
Hello, sir.
Yes.
Sir, I have one question. In the last class, like we did one example in which you told about the FEM formulation for a linear elastic rod under axial load.
Yeah. Yeah.
So there in the governing equation, like we have terms like H transpose Q dx integration. Then we have
Yeah.
terms like minus Q1 and Q2. That
Yeah.
I mean to say that force terms. So
Yeah.
basically, sir, how we will calculate it? Basically, because we are using the formulation in S means the basically the
In
in
the
the
reference.
undefined, yeah, right.
Yeah, reference. Yeah, undefined reference configuration.
Yes, sir. So how we will write the expression for small q as well as minus q1 and q2? Suppose some load is given
Yeah,
and
so
some point.
yeah, they will be see, as far as the small q is there, it is a distributed load per unit original length. So that q has to be given as a load per unit length. So
Okay.
it will be as an input parameter basically. And as far as capital Q1 and Q2 are concerned, if you recall, when I had discussed the very beginning, I think some lecture where I did this problem of truss with this kind of different boundary conditions. So after the assembly at the node points where there are no external nodes, so the contribution of this Q1 and Q2 from the two elements will actually go to 0, and for the locations where there are some boundary conditions, so from the corresponding equation you will evaluate that as a post-processing variable. So that capital Q1 and capital Q2 are not given as an input to the problem, but they are actually found out as the solution after during post processing of the data.
So suppose some point load is given at a node. So
Yeah,
like,
then if there is a point loading, then the difference of Q1 and Q2 would be equal to that point load.
okay, so that will come as it is, sir.
So I had discussed that earlier. So it is same thing basically, For the elastic rod under axial load, the same concepts apply, which I had discussed. I think even I had discussed in dynamics problem also. So it is done in a similar manner.
Okay, sir. Even though the formulation is in undeformed
Yeah,
configuration,
right.
still it works in the same manner.
Yeah, right.
Okay.
So is there any other question? So if there are no questions, let me start. So I think I thought, let me discuss one more example, two-dimensional example. And of course, so we are continuing with the finite deformation. So for no similar kind of formulation, you should be able to do for a plane stress, plane strain element. The way we did for the 1D truss. So I expect you to do for the plane stress, plane strain element. In that you will have basically two non-zero displacements along x and y, u and v, and you will have three strains, Exx, Eyy, and Exy. And the nonlinear terms would be coming in the strains due to displacement u and v in both. So that you should be able to do. I'm not discussing that, but you should definitely try doing that. What I'm discussing, another example is a plate bending example I'm going to discuss. So that is classical Kirchhoff. Oh, I'm discussing classical Kirchhoff plate bending element. So I'm just sketching the schematic of one element. So this is x-axis. This is y-axis and this is z-axis. And this is just one element I am considering. So let us say take a 4-noded element. So the nodes are, this is 1, this is 2, this is here 3, and this is 4. Yeah, so and the load is a transverse load. Yeah, actually see this load can also be deformation dependent, but what I'm going to assume here that although the displacement gradients del w by del x and del w by del y are finite, but they are not that so large that no you have to write q as no, q as a, I mean load vector, external load vector as a function of displacement. So that's an assumption which is actually made over here. So in this theory, you have we have already discussed the plate bending element, classical Kirchhoff plate bending element. So it's the extension of same thing for the finite deformation case. Of course, if the rotations are really very large, then you have other plate theories what are known as Cosrat plate theory and things like that. So I'm not discussing that, but I'm just discussing that del w by del x, del w by del y are finite, but they are within the range so that you can use the plate theory. So this is displacement. If you look at now, only thing is because now we are considering finite deformation. So in plane displacement, because middle surface will also stretch when the plate is subjected to transverse load. So we need to consider the displacements of the points on the z equal to 0 surface. So u as a function of x, y and z is written as u naught, which is a function of xy, that is the displacement along x direction of the points on the middle surface, z equal to 0 surface. And then from the classical plate theory, you already know that this part of the displacement is z into del w by del x. So similarly, the displacement along y direction at any point xyz is given by v naught, which is a function of x and y, minus z into del w by del y. And w, of course, is assumed to be only function of x and y. So w is assumed to be function of x and y. Now, so this is the displacement. So only difference compared to what we have discussed earlier, that we have these two terms. For finite deformation, we need to consider these terms because middle surface is going to stretch. So in the otherwise in a small deformation problem, classical Kirchhoff plate bending problem, we assume that the middle surface does not stretch. So u naught and v naught are taken as 0. Then if you look at the strains, so the non-zero independent component of strains are exx, eyy, and exy. So exx would be equal to the basic definition, as you know, del u by del x plus half of then you have del u by del x whole square plus del v by del x whole square plus del w by del x whole square. So this is a green Lagrange strain tensor as it is. So now what is observed that when the displacement, transverse displacement of the plate is of the order of thickness, so we find that these two terms are actually negligible. And so now if you put this approximation of u here in this, so then you can say that exx will be equal to del u naught by del x minus z into del 2w by del x square, and plus now these two terms are negligible, so in the nonlinear we will have only this half of del w by del x whole square. So this is the final the expression for exx we are using. So similarly now you can write eyy as del v by del y in a similar manner. Now you can write the similar kind of expression for eyy and then make the approximation that derivatives of u and v with respect minus z into del 2w by del y square and plus half of del w by del y whole square. So this is eyy similar to exx. So we are assuming that del u by del y square and del v by del y square are negligible. So you have this approximation. And similarly, twice of exy can be written as del u naught by del y plus del v naught by del x minus 2z into del 2w by del x del y, and plus the nonlinear terms would be del w by del x and del w by del y. The nonlinear terms due to u and v are assumed to be negligible. So this kind of nonlinearity in the literature, if you look at this term which is added in the exx, this term which is added in the eyy, and this is one which is added in exy. So this theory, this based on this saying that u gradients of u, squares of gradients of u and v are negligible, so then only w terms are there in the nonlinear strain. So this theory was first proposed by von Karman. So we call this as that nonlinear terms. Nonlinear terms are based on von Karman assumption. So yeah, once you write this, then rest of the derivations are similar to what so for any problem you should be actually able to do. So now if we look at the strain vector E, I am writing the shear strain as twice, whatever E I am going to write over here. So exx, eyy, and let us say put twice of exy. That is I'm denoting as e. So this will be equal to, now if you look at, I'm grouping the strains in two parts. One is the z, the terms which are dependent on z. So like this term, and this term, they are dependent on z. So the strains are, due to these terms, are varying through the thickness of the plate. Whereas the other set of terms like this term plus this term plus this term, these are giving constant strain through the thickness. So that I'm putting as a membrane strain, and that ones which are giving the strain variation through the thickness, I'm putting as bending strains. So this then you can write it as 1, and with the z minus z term, and then the strains I'm grouping into two parts, membrane strain and bending strain. So epsilon mm, epsilon b. So now if you look at this, let me define what are epsilon m and b. So epsilon m is equal to, now if you look at, I already told you that which set of terms we are calling as membrane strain, which is independent of thickness coordinate. So del u naught by del x plus half of del w by del x square. So these are independent of z coordinate. These the contributions to strain from these are independent of z coordinates. So we are calling them as membrane strain. So del v naught by del y plus half of del w by del y whole square, and then del u naught by del y plus del v naught by del x, and plus you have del w by del x into del w by del y. So this we are calling as actually membrane strain. This is similar to what we already talked about in the Euler-Bernoulli beam element. So membrane strain. And the other is bending. So we are denoting that by epsilon b, and that has these terms del 2w by del x square, del 2w by del y square, and twice of del 2w by del x del y. And we call this as bending or bending strains, or sometimes we also refer to this as curvature. So now you can ultimately, if you look at the variation of E, that is, if you look at this E, this particular E, so the variation of E is delta of E, you can write, because Z is a known coordinate, so 1 and minus Z is a row vector, and into then we will have delta of epsilon m and delta of epsilon b. And now if you look at this delta of epsilon m, delta of epsilon m is going to be the variation of these terms. These terms what we have got here. So this is going to be basically delta of del u naught by del x, and then half and 2 will go, so we will get del w by del x into delta of del w by del x, the variation of quadratic term in the strain, then delta of del v naught by del y plus del w by del y into delta of del w by del y, and then this is del u naught by del y plus delta of del v naught by del x, and plus we will have, of course, delta of del w by del x into del w by del y plus del w by del x into delta of del w by del y. So this will be the variation of membrane strain, and similarly the variation of bending strain delta of epsilon b, in this equation what we have here, will be equal to delta of del 2w by del x square, delta of del 2w by del y square, and twice of delta of del 2w by del x del y. So once we have this, so now let's see what kind of interpolation do we want to use, the interpolation of the variables. So now if you look at, I am assuming that you recall the the non-conforming plate bending element. So I'm going to actually do that. So for the non-conforming interpolation of W, And we have got, of course, the 4 nodes, and at each node the degrees of freedom are, so let us say 4 nodes of the element, 1, 2, 3, and 4. The degrees of freedom are u01, v01, w1, del w by del x at 1, del w by del y at 1. So this will be non-conforming in basically w. You remember we have discussed how this element is non-conforming. So these are the degrees of freedom, 5 degrees of freedom at each node, and corresponding to u there would be 4 degrees of freedom, corresponding to v there would be 4 v0 4 degrees of freedom, and corresponding to w del w by del x and del w by del y there will be 12 degrees of freedom. So when you look at the interpolation, u0 will be can be taken as I going from 1 to 4, ni and u0 I. v0 can be written as I going from 1 to 4, ni v0 I. And w I am writing because w involves these different types of degrees of freedom. So the shape functions, let me write as b. If you remember, we have already discussed the shape functions for w with 3 degrees of freedom, no rectangular element in the physical coordinate space with 3 degrees of freedom. So the method to determine the shape functions is similar. So let us say that corresponding shape functions are m1, m2 up to m12. So m1 into we will have w1, m1 into w1 plus m2 into del w by del x at 1 plus m3 into del w by del y at 1 plus like that we will have. So then the h4, h5, h6 would be corresponding to second node. M4, m5, m6 would be corresponding to second node. So m4 into w2 plus m5 into del w by del x at 2 plus m6 into del w by del y at 2, and like that. So you write all the terms for w in this manner. And now if you look at we need to write the the strains in terms of b and l. So now if you look at the delta epsilon m and delta epsilon b, these two together, so I am putting both the variations together. So you will have two actually set of the terms. One is the linear terms, and other would be nonlinear terms. So now as far as the degrees of freedom are concerned, so you will have u01, v01, w1, del w by del x at 1, del w by del y at 1, and then second node u02, v02, w2, del w by del x at 2, and so on. So that's what the degrees of freedom are going to be. So in if you remember, look at this delta of epsilon m. So we have linear terms. As far as linear terms are concerned, only this is the linear term in delta epsilon m. So that is corresponding to basically u0. So you will have del n1 by del x, and then the remaining 4 degrees of freedom are corresponding to other variables. Then you will have del n2 by del x, again the 4 degrees of freedom corresponding to other variables, del n3 by del x 0 0, then del n4 by del x 0 0. So this is what is going to be here, of course, because we are writing delta epsilon m, so with the degrees of freedom there would be delta, variational symbol delta. So here everywhere there would be delta. So the variational operator is going to be there. Okay. So then similarly the second term, that is basically this term in the linear part, it is going to be there. So 0 del n1 by del y, that is corresponding to v, 0 del n2 by del y, del n3 by del y. No, you can write like that, del n4 by del y. And then the second term, linear term in the membrane strain is these two terms that involves both u naught and v naught. So we will have u naught derivative with respect to y, so del n1 by del y, and v naught derivative is with respect to x, so we will have x, then 0 0, and then del n2 by del y, del n2 by del x, and 0 0, and so on. No, you can write in a similar manner. Then the no, in the linear part, if you look at now epsilon b, so we have delta of del 2 w by del x square. So that goes with the degrees of freedom w1 del w by del x and del w by del y and so on. So first two would be 0, and then we will have uh, del 2 m1 by del x square, del 2 m2 by del x square, del 2 m3 by del x square, then the 0 0, and then we will have del 2 del 2 m4 by del x square, and so on. No, you can write no, similarly the other terms, and similarly the other two curvature terms you can write in a similar manner. You can write those terms in the similar manner. So this is how we will write the linear part, and this is what we call simply as B, linear strain displacement relations. Then in this you will also have the nonlinear terms. So now if you look at the nonlinear terms, so we are going to have these degrees of freedom. So delta of u naught 1, delta of v naught 1, delta of w1, delta of del w by del x at 1, delta of del w by del y at 1, then delta of u naught 2, delta of v naught 2, delta of w2, delta of del w by del x at 2, and so on. I am not writing all the terms. No, you can write in a similar manner. So now the nonlinear terms, if you look at, they are there only in membrane strain epsilon m. So if you look at the delta epsilon b, there are no nonlinear terms. There are only linear terms. But here we have, so this is a nonlinear term in no x component. This is nonlinear term in y component, and these are in the exy component. So now if you look at, we will write this as 0 0. U and v do not contribute. And then we will have no derivative with respect to x. So del m1 by del x into del w by del x, and then del m2 by del x into del w by del x, and del m3 by del x into del w by del x, and then two zeros will be there corresponding to u and v, and then we will have del m4 by del x into del w by del x, and so on. No, you can write the remaining term in a similar manner. So in the second row we will have derivatives with respect to y. So del m1 by del y into del w by del y, del m2 by del y into del w by del y, del m3 by del y into del w by del y, 0 0, and then del m4 by del y into del w by del y, and so on. And the last, no, the third row, the terms are going to be del m1 by del x into del w by del y, plus we will have del m2 by del y into del w by del x. No, this is both are m1. The first term, this is m1, and then no, you can write the other terms. The there are no nonlinear terms in the bending terms, so they all will be 0. No, you can put them. The bending terms in the bending terms there are no nonlinear terms. So this matrix we call it as BNL, and this is a vector of elemental degrees of freedom, so this is delta dE. So you can say ultimately that delta epsilon m and delta epsilon b is equal to b plus bnl. So I have defined b and bnl into delta dE. So you can write it like this. Now if you look at this delta E vector which we have defined, so that is basically 1 minus z, this row vector, into delta epsilon m, delta epsilon b, and this can be written as 1 minus z, and this can be written in terms of b plus bnl, and then into delta of dE. So this is how you can write these terms. And now similarly, now if you also want to write delta E, the increment in E, so increment in E would be written as 1 minus Z into B plus BNL, and instead of variation symbol we will have increment delta DE. So this is the increment will be there. Now we want to develop the element level governing equation. So let me start with the principle of virtual work. Although no, you can start from the what we have derived the for general case, you can also start from there, but I am starting with the principle of virtual work. So the integration over reference volume, and then we have that is delta of no, E transpose into this S, and both E and S have three components, dV naught minus integration over the reference area, so A naught delta W transpose Q into dA, and there would be internal load vector, so that I'm just writing as delta D transpose into F internal for the element. So this is actually equal to 0. So this is the principle of virtual work written in this manner, and now you substitute delta of epsilon E and delta W etc. in terms of interpolation functions. So you can write this integral over area, you can split integration over the thickness. Reference area, let me put as just A itself. A is the capital A is the reference area, so I'm removing A naught over here, just say A. So this is then going to be delta E transpose, we have seen here 1 minus Z B plus BNL into delta DE transpose. So when you take transpose, it would become delta DE transpose, and then we will have B plus BNL transpose, and then we will have 1 minus Z transpose, so it will become a column vector. So we will have 1 minus Z as a column vector, and then you have this stress dz dA. So that's this term minus integration over area, reference area, and then I'm writing W as HW into dE. HW is the interpolation corresponding to W, so we will have delta of D transpose into HW transpose into QDA. And of course this internal force term remains same without any integration. So you will have delta of D transpose into F internal for the element. This is equal to 0. So now from this we develop the element level governing equation, because delta D is arbitrary. So then the coefficient of delta D has to be basically a null vector, and from there we'll get the element level governing equation. So for arbitrary delta DE, we get the equation which we call as element level governing equation. So integration over area, integration over thickness minus h by 2 to plus h by 2, that's the reference, the original thickness. So we will have B plus, in the undeformed configuration whatever thickness is there, transpose 1 and minus Z, and then you have this S dz dA minus integration over area, and we have this HW transpose QDA, and minus we will have F internal for the element. This is equal to a null vector. So this is element level governing equation, and which is non-linear as we know. Element level. So you see how the straightforward for different problems you can write this element level governing equation. And this is non-linear, so we solve using Newton-Raphson method. So for that we need to write the incremental form. So if you look at the incremental form of element level governing equation, incremental form of element level governing equation. So using Taylor series. So we do that. So we have done earlier. So it's a similar thing. So now if you look at integration over area, integration over thickness, h by 2 to h by 2. This side we have B plus BNL transpose. Then we have this 1 minus Z column. And then we are going to write delta S, that is capital delta S. And that is a function of E. So we can write that as del S by del E, this matrix. And then delta E, and delta E is 1 minus Z into B plus BNL. We have already written this expression. And then let me first put the integration and put the delta D outside. And this is evaluated at the previous iteration into delta DE evaluate for the current iteration, that is for I plus 1. So that's the first term. And the second is integration over area, integration over minus h by 2 to plus h by 2. And then we take the increment of the first term itself in the equation, that is this equation. So B is anyway constant, so its increment is 0. BNL will have non-zero increment. So we will have delta BNL transpose, and we have 1 minus Z. And if you see, this formulation is quite similar to what we did for the Euler-Bernoulli beam element. So I, then we have dz dA, and this is evaluated of course at I plus 1. So that's one term. And then of course the very first term of the Taylor series. So we will have integration over area, integration from minus h by 2 to plus h by 2. And then we have this B plus BNL transpose into 1 minus Z, and then we will have this S dz dA, whole thing evaluated at previous iteration. Minus we have integration over area, HW transpose into QDA, and minus F internal for the element. This whole thing is equal to a null vector. So this is the incremental form of the element level governing equation what we have got over here. Now just a few things about the constitutive relation. So we are again assuming that even for the finite deformation case, the the relationship between stress and strain is linear. So I am assuming that stress strain relationship is linear elastic isotropic material. So it would be a constitutive matrix C. And for linear elastic isotropic material under plane stress condition, this is equal to 1 minus nu square. And then we have 1 nu 0, nu 1 0, 0 0, 1 minus nu by 2. So this for the plane stress case. So now if we want to look at the various integrations. So here if you look at, we have this matrix over here. So now if you look at this matrix, so let me just run through the thickness integration, because that part is only function of Z. So integration from minus h by 2 to plus h by 2, we have 1 minus Z, and then we have this del S upon del E, which we said as C, and then we have 1 minus Z dz. So this you can write as This you can write, as you see, can be written as basically the integration from minus h by 2 to plus h by 2, and this is C matrix. So if you multiply, we will have basically, C you can take with either the left side this Z matrix or the right side Z matrix. So when you multiply these, you will get this C, then minus Z into C, minus Z into C, and Z square into C. So this is what you will get, and dz after this multiplication. Del S by del E, this is equal to actually C. And if you do the integration, because Z equal to 0 surface is the middle surface, so the integration from minus h by 2 to plus by h by 2, this integration will just give you thickness. So the first term will simply become h into c. This integral would be actually 0, z square by 2, and when you put these limits, so that integral would be 0. This is also 0, and then here you will get h cube 12 by c. So this is what you will get. Usually what we do in the literature of plate bending problem, this A, we know the first h into c is denoted as A, extensional stiffness matrix, and D is the bending extensional stiffness matrix, bending stiffness matrix. And let us say this is going to be 6 by 6 matrix. See, this is 3 by 3, this is also 3 by 3, 3 by 3, this is also 3 by 3. So overall this is going to be 6 by 6 matrix. So let us say it is C bar, which is 6 by 6. Here A is H into C. As you see, A is H into C, and D is H cube by 12 into C. This is extensional stiffness coefficient matrix. So there is a name for this. A is known as extensional stiffness coefficient matrix, and D is bending stiffness coefficient matrix. So yeah, that's the, so now based on these assumptions, and we will also say that the integration, now see, from integration from minus h by 2 to plus h by 2, and this one minus z into, yeah, I was writing the square brackets, although that's a column vector essentially. So into this s dz is written as basically in terms of integration of s through the thickness is I know the stress resultant, so that is denoted as n, and integration of minus z into s from a minus h by 2 plus h by 2 dz is denoted as moment resultant. So we can write this as n and m, where n is stress resultant, in plane stress resultant. So here n is referred to as in plane stress resultant, and m is known as moment resultant. Yeah, so you write these quantities like this. So once you have this, so you can see the final incremental form would be, can finally be written as basically integration over area, and then we have this B plus B NL transpose into C bar. अभी मेरी क्लास चल रही. So this is B plus BNL integration over area, and this is evaluated at the previous iteration. Into we'll have delta of the the incremental delta. So delta of DE for the current iteration, plus the second term we can write integration over area, and delta BNL transpose, and then we have this N and M here into dA. This is evaluated at previous iteration and this is evaluated at current iteration. So yeah, this is after now we carry out the through the thickness integration. So we write it in this form: minus integration over area. We have HW transpose into QDA, and then we have minus F internal for the element, and this whole thing is equal to a null vector. So that's the final form. I have already defined know what are n and m. So n as I said over here, that the integration of S is having three components, no, SXX, SYY, and SXY. So that means say this N will have three components, NXX, NYY, NXY, and similarly M will also have three components, MXX, MYY, and MXY. So now let's see.
Another term will be there, sir.
Yeah, which term? Yeah, I think I missed one. Yeah, I missed that. Yeah. So let me write that term also. So here you'll have plus integration over area, and yeah, that's a vector. So we will have B plus B NL transpose, and then we will have this N and M dA. This is evaluated at P. So yeah, this term will be there. Thanks for pointing it out. So this term will also be there. No, you'll have to keep this in mind. So this is just coming from what we have written over here. So essentially, this thing. Only thing, the thickness integration is explicitly put. So finally, you get in this form. And now only thing what remains is the this term. So this particular term, how do we write no in the form of kg matrix into delta dE? So if you look at this term, so let us consider this integration. We have integration over area, and then we have this delta BNL transpose, and then you have this N matrix and M matrix. This is evaluated at I, this is evaluated at I plus 1 into dA. The increment part is evaluated at previous iteration. So actually what you can do is, as you see in the delta BNL, the last three rows are null vectors. So their product with M will be a null vector. So you will be left with only three rows, first three rows, which are multiplied with NXX, NYY, and NXY. So you would see that you would be able to rewrite this. This term can be rewritten as the integration over area, and then the derivative of W with respect to X and Y, and the interpolation of W is written as HW into DE. So this would become del HW by del X, del HW by del Y transpose, and then you will have N will have NXX, NXY, NXY, and NYY. So these are the N components. CM will not come, as I already said. The last three rows of delta BNL are actually null rows. So this will be del HW by del X, del HW by del Y, dA. So this is your Kg matrix, which is evaluated at previous iteration into delta dE I plus 1. So this is how you can write this term. Finally, so this is what we call it as actually Kg. So this whole matrix, you call it as KGE of at the ith iteration. We also call it as geometric stiffness matrix, and this is coming from basically the nonlinear part of the strain, del W by del X square, del W by del Y square, and del W by del X into del W by del Y. So from there, you can rewrite this matrix like this. And here, your HW is when you interpolate. So now if you write the W, so let me define what HW is. So you will write it in terms of U0, V0, the terms are 0. Then you will have M1, M2, M3, 0, 0, and then you will have M4, M5, and M6, 0, 0, and then similarly, you will have M7, M8, M9, 0, 0, and so on. Into you will have DE. So we write W is equal to, this is what is referred to as HW, no, this matrix, into you have DE. So that is where no this HW is coming. So I think, yeah, so this is what I wanted to. So other for, as I said, for plane stress, plane strain elements with displacements U and V and the nonlinear terms in the strain as del U by del X whole square, del U by del Y whole, del V by del X whole square in X, and in Y strain you will have del U by del Y, del V by del Y whole square, these terms. So you should be able to derive. So for any other problem, you should be able to derive the element level governing equation. And of course, rest of the solution procedure is that you assemble, impose a boundary condition, solve, and now continue the iteration till the solution converges. And the convergence criteria, of course, could be put in the form of a residual force norm, second norm of residual force, divided by the the second norm of the external force, and that is within, if it is within certain limit, you say that the solution has converged. Or you can check the increment in the individual degrees of freedom. If that is less than a certain number, then no, you say that the solution is converged and you stop over there. So yeah, I think this is what I want to discuss today. So I want to stop here. The next class I will be starting, I want to discuss little bit on hyperelasticity. Different, how we have the strain energy density function postulated. So how do we develop the element level governing equation, and how typically the hyperelastic model is formulated. So I will be discussing that in the next class. So I now want to stop here. If you have any doubts and questions, now you can ask. So anybody, any doubt, question on what we discussed today?
Hello, sir.
Yeah.
N will be a column vector or it is a matrix?
It is a column vector. N is a column vector.
Then in next step, in kg expression, how it is nxx, nxy?
No, then because there are three components, no, nxx, nyy, and nxy. So you are rewriting this. You have to rewrite this. So first, no, you take delta BNL elements multiplied with n, and then rewrite such a way that one side you have this W terms, another side you have this delta W term. Delta W is written in terms of derivatives of say function, and delta D. So n is a column vector, nxx, nyy. So if you look at n is a column vector, nxx, nyy, and nxy. And similarly, m is a column vector, which is mxx, myy, and mxy. This is rewritten, so it is not direct. From here to here it is not direct. You have to first multiply this delta BNL with elements of n, and then you have to write such a way that one side you get these say functions derivatives, the other side you get the derivatives of the shape functions and delta DE. So delta DE you want to take on the right hand side. So there is some manipulation is involved over here. So I know if you multiply this, open it up, multiply, and then rearrange, you will be able to do in this form. Okay? Hello?
Yes, sir. Yes, sir. Okay.
So are there anybody, any other question? Okay, so if there are no, please go through all of these actually, and no, you should, unless and until you do derive the intermediate steps you complete, you won't be able to basically understand. So you have to put some effort in, after each lecture you should put some effort, and then you can ask any doubts and questions you have on any of these formulations. So yeah, but you must go through all of this yourself. So if there are no doubts and questions, I am stopping. Thank you all for your attention.